All right, buckle up, everybody. We're about to embark on a thrilling saga. An epic battle, really. One fought not on a battlefield, but in the microscopic world of our cells.
Ooh, sounds exciting. I'm ready. Where are we headed today?
Today's deep dive plunges us into the intricate realm of monoclonal antibodies, those tiny protein warriors engineered to fight disease.
I know a bit about mAbs, but this sounds like more than just a general overview. What's the specific focus?
It's all about the challenge, the
Hmm.
real nail-biter, of creating effective mAbs against something called M&S blood group antigens. Imagine trying to design a key for a lock that constantly changes shape. That's the kind of puzzle scientists are grappling with.
M&S blood groups. That rings a bell. Didn't some early attempts using peptide targets completely flop?
Exactly. They tried, they really did, but those early attempts just wouldn't bind to red blood cells. It was a huge setback, a scientific head-scratcher, you could say.
Hmm. And I bet there's a fascinating reason why those initial efforts hit a brick wall. What was happening at the molecular level?
So picture this. You're a scientist, all set to design this perfect mAb, this guided missile, to hit a specific target on a protein.
Okay, I'm with you. I've got my lab coat on, metaphorically speaking. What happens next?
And then you realize the protein you're targeting is like a jellyfish.
A jellyfish? What do you mean?
It's constantly changing shape. It's a slippery, elusive target. And these shape-shifting culprits are called intrinsically disordered proteins, or IDPs for short.
IDPs, that's right. They're notoriously difficult to target. It's like trying to pin down well, you already said it, a jellyfish.
It's a fantastic analogy, really captures the essence of the problem. So how do you design an antibody that can effectively bind to something that's constantly in motion? You can't just throw your hands up in defeat, right?
Definitely not. Scientists love a good challenge. And in this case, they came up with not one, but two rather ingenious strategies.
I'm on the edge of my seat. Lay it on me. What did they come up with?
All right, so imagine you're back in that lab, staring down this frustrating IDP.
Okay, got it. Lab coat IDP, go on.
One strategy was to say, okay, fine, you want to be a jellyfish. Let's give you some more structure, make you a little less wobbly. They called this peptide extension with linkers.
Uh-huh. So it's like giving the jellyfish a little backbone, trying to make it more predictable.
Hmm.
But did they just go about this randomly? Or was there a method to this madness?
Not at all. They actually tapped into the power of computers using some sophisticated software like PP2D and Rebeta that could actually simulate these extended peptides, see how they might behave in a virtual world.
That's cool. So they had a virtual lab, testing things out before actually getting their hands dirty. Makes sense, right? Saves a lot of time and resources.
Exactly. Simulations like these can offer valuable insights and really guide the experimental process. Of course, they have limitations, but they're a powerful tool in the researcher's arsenal.
I can imagine. So let's talk about the second strategy. It sounds like they went for something completely different this time.
Oh, they did. This one, known as the Sormani method, took a much more cunning approach. They thought, okay, if this IDP wants to play hide and seek, we'll just force it into a shape we can recognize.
I like where this is going. So instead of trying to pin down the jellyfish, what did they do?
They used a complementary peptide, almost like a piece of molecular Velcro, to force the target protein into a more stable structure, a beta sheet.
Wow, that's clever. Talk about outsmarting a shapeshifter. But how does this Sormani method actually work? Take me through it step by step.
Okay, so picture this. The scientists start by determining the amino acid sequence of the target protein, the slippery IDP they want to catch.
Right, they need to know its code, its blueprint, so to speak. Then what?
Then they turn to a massive database, think Library of Alexandria, but for protein structures, called the Protein Data Bank. And they search for similar protein structures, ones that already exist in this nice, stable beta sheet formation.
It's like they're looking for a pre-existing solution, something nature has already figured out that they can adapt for their own purposes.
That's a great way to put it. They're looking for the perfect fit, a structural twin, even if they have to combine bits and pieces from different structures. It's a bit like a molecular jigsaw puzzle. And once they found the right sequence, they attach this complementary peptide, this molecular Velcro, to the antibody.
Amazing. So they've essentially created a trap, a way to lock the IDP into a predictable shape. And why is this complementary peptide so effective? What does it actually do?
Remember those MNS blood group antigens we talked about earlier? Well, in this case, they were targeting specific ones called the GNU and U antigens. And these, like many other disease-related targets, are these slippery IDPs. But by attaching the complementary peptide, they could actually force them into the desired shape for recognition. The antibody now has a much easier time binding.
It's like they've given the antibody a handle, something it can grab onto. So did these strategies actually work? Do they see any positive results?
The early results are actually quite promising. They've managed to identify several sequences capable of forming those stable beta sheets and have successfully grafted those onto antibodies.
That's fantastic news. And it makes you think about all the potential applications. You mentioned MNS blood groups earlier. Why is targeting those specifically so important?
Well, think about blood transfusions. If you have effective mAbs against these MNS antigens, you can improve blood matching. You can reduce the risk of those dangerous immune reactions.
That makes sense. It's about making transfusions safer and more effective. But I imagine the applications go way beyond just blood transfusions, right?
Absolutely. This has huge implications for developing more effective therapies for a whole host of diseases. Imagine targeting cancer cells or tackling autoimmune disorders with these highly specific
The
antibodies.
possibilities seem almost endless. It really highlights the creativity, the ingenuity that goes into this kind of research. It's inspiring, really. And it leaves you wondering, what other innovative approaches will they come up with next?
Who knows? Maybe they'll find a way to predict exactly how these IDPs will fold, design even more targeted therapies. The quest for the perfect mAb is far from over, and I, for one, am excited to see what the future holds.
Me too. It seems like we're just at the beginning of a very exciting journey in the world of mAb research. Thanks for joining us on this deep dive. Until next time, keep those scientific minds curious.